In the first screencast in this series, we defined 5 requirements of walking based on the earlier work of Perry and Gait. In the last one, we looked at the requirement for energy-efficient walking and saw how that leads us to rely on an inverted pendulum mechanism to move our body forwards through the stance phase. This results in a gait pattern that's almost identical to the compass gait that Inman and Eberhardt took as the starting point for their work on the determinants of gait. To start this screencast, we'll first look at how compass gait is represented in the gait graphs. First of all, there is no double support phase. To understand this, let's look at a picture of double support. If the knees don't bend, then you can see that the legs form a triangle. If the feet remain fixed in the same place, then the hips can only be in one position. Thus, if the feet are stationary, the hips must be stationary, and the body can't be moving forwards. As we saw in the last screencast, however, in order for the inverted pendulum to work, the body has to be moving forwards at foot contact. The only way this can be achieved is if the trailing foot leaves the ground at the precise instant at which the leading foot makes contact. In other words, there can be no double support. If there is no double support and the gait is symmetrical, then the foot off must occur 50% of the way through the gait cycle. We've also noted in an earlier screencast that if walking is symmetrical, then the gait graphs for the left side lie exactly on top of those for the right side, which will thus be hidden from view. We will only see one trace in any of the graphs in this series of screencasts. As noted in the screencast, the trunk remains upright throughout the gait cycle, but because we define the transverse plane of the pelvis as that containing the anterior and posterior superior iliac spines, this pelvis is recorded as being tilted about 14 degrees anteriorly. In compass gait, and in order to allow the trunk and head to remain upright, the hip extends through stance and flexes through swing. The femur movements are symmetrical about the vertical, but because the pelvis is tilted forwards, hip movement is recorded as about an average value of about 14 degrees of flexion. There is no knee movement in compass gait by definition. In stance, the foot is in contact with the ground and the sole thus remains horizontal. As the leg is pivoting about the ankle, however, the ankle must start off in plantar flexion, move through neutral, and end up in a position of dorsiflexion at the end of stance. The range of movement will match that of the hip exactly. During swing, the plantar surface of the foot still remains horizontal as it slides along the floor. As the pattern of hip movement is reversed, then the pattern of ankle movement must also be reversed. For those of you familiar with gait analysis, the fifth is an extra graph that we don't normally output. Over recent years, however, I've become more and more convinced that we should be printing this graph of where the foot is in relation to the ground. In compass gait, as the plantar surface of the foot is always horizontal, this foot angle will always be 0. Looking at the graphs, you'll see that compass gait gives quite a reasonable picture of normal hip and pelvic movements, but is not particularly convincing anywhere else. To start to understand why the other graphs are so different, we need to understand how movement is modified to achieve the other requirements of walking. We'll start off by looking at clearance in swing. To explore this, we're going to use eVern. If you're viewing this in PowerPoint, then you should be able to move Vern's body segments by dragging on them with a mouse. If you're watching the video version, then you won't be able to, but you can go to my blog, www.richard.net, and find an interactive version of eVern there that you can use. If you play around with Vern, you'll start to notice several things. The first is that the foot sticking out in front of the leg causes a real problem. If you just move the hip backwards and forwards, then you'll notice that the toe will hit the floor for a considerable range of hip movement. If the knee and ankle are in a neutral position, then this range is from 9 degrees of hip extension to 14 degrees of hip flexion, a total range of 24 degrees. If you flex the knee by a small amount, say 10 degrees, then things actually get worse, with the toe catching between 7 degrees of hip extension and 22 degrees of hip flexion, a range of 29 degrees. Note that I've coloured the figure blue to indicate that these are static images that you can't interact with them as you can with eVern. If you play around with eVern further, you should be able to discover the minimum knee flexion that allows the toe to clear with the ankle in neutral. It's about 50 degrees. So here's an important message. If you want to use knee flexion as a mechanism to achieve toe clearance, then you need quite a lot of it. There's no point just flexing your knee a little bit. Small amounts of knee flexion actually make toe clearance more difficult. Also notice that to clear the limb at this point, the hip needs to be more flexed than it would be if the knee were fully extended. Using knee flexion as a mechanism to ensure toe clearance not only requires quite a lot of knee flexion, but it also requires earlier hip flexion. So let's put this together in the graphs. Minimum toe clearance occurs about halfway through swing. If we want to use knee flexion as the primary mechanism for ensuring toe clearance, then we need a lot of it, at least 50 degrees. We also need to have the hip flexed reasonably early in the swing phase. You'll see from the normal gait data that this is actually the case. The hip reaches its maximum flexion at shortly after halfway through the swing phase during normal walking. The ankle must be at least in neutral. Some dorsiflexion will help, but only if there is a good degree of knee flexion to start with. It cannot be used to substitute for small amounts of knee flexion. The pitch of the foot will follow the knee, moderated to some extent by the hip flexion. The next screencast builds on this process by considering the requirements of adequate step length. So make sure you've understood how we've arrived at this set of graphs before you move on. So how are we going to apply this clinically? The main thing to notice is the large degree of knee flexion that is required if it's going to be used as the primary mechanism for assuring clearance. If you want your patients to walk normally, then you need them to be able to achieve at least 50 degrees of knee flexion. The main message is thus to work hard to enable this. We've seen, however, that moderate amounts of knee flexion can actually make clearance more difficult than walking with an extended knee. Patients who can't flex the knees will just not be able to walk normally and will have to be encouraged to use compensatory strategies to enable them to clear at all. It's important to recognise that for this group of patients, as with so many, normal walking is not a realistic goal.